Well, I made my stupid handwriting example in the way, but we'll just have to figure that out. So if you use your calculator, that works out to be, and I used to know this off the top of my head, but 22 minus 15.25 is 6.75 squared. It's 45.56 divided by 15.25, 2.987. So let's just round that up. Two significant digits, it's probably fine, by the way. 2.99. This entry in the chi-square would be observed 17 minus expected 30.5 squared divided by 30.5. That's going to end up being, I can't remember what it is, and it doesn't matter. 17 minus 30.5 is negative 13.5. Divided by 30.5. So this gives me essentially 5.96. Hope I'm doing this right. Okay. And then this one actually turns out to be the same as the other. So this would be our observed 22 minus our expected 15.25 squared over 15.25. And again, this formula is right there. To get the chi-square test statistic, we just have to add up those numbers that we just calculated. So let's go back to our thing here. So that's going to turn out to be the same, 2.99, let's say. And you add those up. I get 11.94. So what is the chi-square value? Chi-square value is that. It goes right there, 11.94. If you didn't show all of this work and you just wrote a number here, but you forgot to like square one of these things or something, like you had it all laid out and you just did some obvious math error, you'd still get partial credit. If you just wrote 6.23 here, no work, no partial credit. There's nothing I can do. All right, what are the degrees of freedom? So degrees of freedom are number of categories minus 1. Here we have 3 categories, red, blue, and purple. 3 categories minus 1 equals 2 degrees of freedom. What is the p-value? So this is the part at 11.94 with 2 degrees of freedom. So let's go back to our chi-square table. And for some reason it's not letting me write on this because, so I'm just going to go ahead and make a new layer. Okay, I'll go switch to red just for fun. Our chi-square value was, I think, 11.94. Right? Yeah, there it is. Okay. And our degrees of freedom were 2. Okay. So here's 2 degrees of freedom. So that's the row that we want. And what we want to do if you're using a table, now, I mean, in the real world, actual statisticians don't use these stupid tables anymore, really. We actually calculate the chi-square p-value based on probability distributions. But for the purposes of genetics, let's just use the table. What you want to do is you want to go find the closest approximation to your chi-square value and then go up to see what p-value it corresponds to. So these are the chi-square values that you're looking at. They're very low, so we keep going to the right and you can see how they get larger. 0.211, 1.386, 4.6, still bigger. Our chi-square value actually lives to the right of the highest chi-square value for 2 degrees of freedom that is on this table. this chi-square of 10.597, which we exceed, corresponds to a p of 0.005, and as you go this direction, p gets smaller. So what can we infer? If we have this is 11.94, our p-value is less than 0.005. All right? If our chi-square value were somewhere in between these two, we could say our p-value, for example, if it was right here, we could say our p-value was somewhere between 0.05 and 0.025, but it's not. So our p is less than 0.05. So let's go back to our problem. And we'll go back to our answer layer here. P is less than 0.005. That's the correct answer. Here's the interpretation. Do the observed data deviate significantly from expectations? Now, we went over this in class. What does significantly mean? And Fisher came up with this. Well, I don't know if it's less than a one chance in 20. It's probably significantly different. And that's where we got p, 0.05 equals a significant difference. And so that's the cutoff that we'll adopt in our class, even though we recognize it's somewhat arbitrary. So if p, the probability of observing this difference between our observed and expected outcomes is, just by chance alone, is less than 0.005. It's extraordinarily unlikely to observe for our hypothesis to be true, and this difference that we observe between we see between observed and expected to have just occurred by chance. So that says our hypothesis, our data deviates significantly from those predicted by our hypothesis. So the answer here is yes. We'll do a few more chi-square problems in subsequent videos, and we'll sort of keep doing this. And then if you're enrolled in 315, you're going to do this kind of stuff a lot with your Drosophila. And so you'll get it kind of cemented in your head. Many of you have had Stats 250 or 251, so you understand the concept of a p-value. Probably could explain it better than my bumbling explanation from a minute ago. But if you don't, and you're really sort of struggling with this, either say so at the beginning of class and we'll go over it. Remember, we have a review session before every exam, so we can explain it then. Or you can come to my office hours, or later on when I'm doing this kind of stuff and people might be watching live, they can get into the chat channels and say, hey, explain that again, I don't understand it. Okay? So what we just did is we walked through a super simple transmission genetics problem. We were testing the hypothesis of incomplete dominance, and I had you just structurally lay out what's the predicted phenotypic ratio, here are the observed data, convert this phenotypic ratio to expectations, and conduct a chi-square test. And this is coming on the exam, folks. And you're going to need to know how to do this. So if you have any questions, just let me know. All right, I'm going to figure out how to turn off this weird game show app thingy. Anyway, more